Imagine deploying an AI model to catch credit card fraud. Like in the lab, it hits 99% accuracy. You pop the champagne, push it to production, and within a week, it cost your company millions of dollars.
Yeah, that happens a lot more often than you'd think.
Right. So today, we're doing a deep dive to extract the core insights from a really comprehensive guide on scikit-learn. We need to figure out why a perfect model is, well, usually a cheating model.
Exactly.
Okay, let's unpack this. Building an AI model is a lot like cooking, right? You can't just toss raw, unpeeled data into an algorithm and expect a gourmet prediction.
No, definitely not. And scikit-learn is the gold standard for this kind of classical machine learning in Python. You aren't grabbing it to build massive data-hungry neural networks.
You're not building the next ChatGPT with it.
Exactly. If you're doing complex image recognition or something, you're living in TensorFlow or PyTorch. But for everyday tabular data, the kind that runs most businesses' scikit-learn is the undisputed champion. It's incredibly reliable, provided you have the statistical discipline to use it correctly.
So let's jump into those mechanics, starting with the preprocessing trap. Because the guide makes it clear that feeding raw, unscaled data into certain algorithms is just, asking for a disaster. Why does raw data fail?
Well, it really comes down to things like the standard scaler, especially when you are dealing with distance-based algorithms like support vector machines or k-nearest neighbors.
Okay.
Those models rely on calculating the literal Euclidean distance between data points. So imagine a data set where one feature measures a simple 1 to 10 score.
Yeah, like a customer satisfaction rating or something.
Right, and then another feature measures revenue from, say, 10,000 to 100,000.
Wait, let me stop you there. Isn't the algorithm smart enough to just, assign a lower weight to the larger numbers during the training phase?
Yeah.
Why do we have to handhold it?
It is a totally fair question, but no. The math is initially blind to your context. That massive 100,000 feature mathematically dwarfs the 1 to 10 feature in the distance calculation.
Oh, wow. So it just bulldozes it.
Pretty much. The model practically ignores the smaller feature entirely. Now, tree-based models might not care, but for an SVM, you have to use a tool like standard scaler to force every feature to a mean of 0 and a standard deviation of 1.
You have to mathematically level the playing field.
Exactly.
Okay, so standard scaler fixes the math for the features going in, but what about the predictions coming out? Like, if the data is inherently skewed, like our credit card fraud example earlier, doesn't the math get dominated by the majority class anyway?
Yes, and you just hit exactly on the accuracy paradox.
The accuracy paradox.
Yeah, so if 99% of transactions are perfectly valid and only 1% are actual fraud, a completely useless model could just hard code a valid guess every single time.
And it would technically achieve 99% accuracy.
Exactly.
So what does this all mean for us? Should we just throw out accuracy altogether when measuring success? Because honestly, it sounds like the algorithm is just doing exactly what we asked it to do, right?
Yeah.
Optimize for the highest overall score. The problem is our business logic.
What's fascinating here is, well, you're exactly right. The algorithm is ruthlessly optimizing for the metric you gave it, which is why you have to change the rules of the game.
Ah, I see.
The source material points out that for imbalanced data, you abandon overall accuracy and you look at PRAUC, which stands for Precision Recall Area Under Curve.
Okay, walk us through how that actually changes the math under the hood.
So precision asks a specific question. Out of all the cards we actually froze, how many were legitimately stolen? And recall asks, out of all the real fraud out there in the wild, how much did our model actually catch? You combine those metrics with class weights, which severely penalize the algorithm mathematically for missing that tiny 1% minority class.
So you force the model to prioritize the rare event.
Yeah, exactly.
But here's where it gets really interesting, because even if you get your PRAUC dialed in, the guide talks about a total disaster scenario where your model still fails in production. We hinted at this in the intro.
Yeah, data leakage.
Oh.
It is the silent killer of machine learning models. Let's go back to standard scaler for a second.
Okay.
A lot of practitioners will scale their entire data set first and then split it into their training set and their testing set.
Wait, which ruins the test set, right?
Yeah.
Because the test set is supposed to be a completely blind exam.
Precisely. If you scale everything together, the mathematical mean and variance of the test data accidentally leak into the training phase.
Oh, I see. So the model is effectively peaked at the answers, or at least the statistical distribution of the exam before taking it.
Yeah, it's essentially cheating.
Okay, but practically, how do we stop the cheating? You have to scale the data at some point.
Right, and scikit-learn solves this elegantly with a feature called pipeline. A pipeline actually chains your preprocessing and your estimator together.
Oh,
When you run cross-validation, the pipeline ensures that the actual learning of the mean and variance is only ever calculated on the training folds. It strictly applies only the transform method to the test data.
so it mathematically quarantines the test data. So the model genuinely encounters the test data blind
Yeah.
using only the math it learned from the training data.
Exactly, because in the real world, you have to scale tomorrow's data using yesterday's math.
That makes total sense. And whether you're managing a tech team or just insanely curious, understanding concepts like data leakage protects you from trusting a fundamentally flawed model just because a dashboard flashes a high score.
Yeah, and if we connect this to the bigger picture, it proves that machine learning isn't just about calling a predict function in Python. It requires strict statistical discipline.
Absolutely. Which leaves me with this final thought for you to chew on. If scikit-learn requires strict pipelines to prevent future data from leaking into its learning process, how might we build mental pipelines in our own lives? Like, how do we stop hindsight knowing how things eventually turned out from leaking backward and altering how we evaluate our past decisions? Nobody wants to rely on leaked assumptions.